In the last lesson, we learned that acids are proton donors and bases are proton acceptors. We also learned that acids and bases exist as conjugate acid-base pairs. Now we move on to find out, how do we measure the strength of an acid or a base? Acids ionize in water. For example, hydrogen chloride molecules react with water molecules releasing hydronium and chloride ions. When hydrogen chloride molecules come into contact with water molecules, their hydrogen atoms are so strongly attracted to the water molecules that the hydrogen chloride molecules split apart. The chlorine atom forms a chloride ion by accepting the electron from the polar covalent bond between hydrogen and chlorine in the hydrogen chloride molecule. Chloride ions are hydrated by water molecules and float relatively freely in water. The hydrogen ion attaches itself to a water molecule, forming the hydronium ion. Hydronium ions are also hydrated by water molecules. Hydrochloric acid is a strong acid because 99.9% of its molecules ionize in water. Strong acids ionize almost completely in water. What does this mean? How does the extent of ionization cause hydrochloric acid to differ from a weaker acid? Ethanoic acid is a weak acid. Many of its molecules remain in their molecular form when ethanoic acid mixes with water. The double arrow in the ionization equation shows that a chemical equilibrium is set up when ethanoic acid ionizes in water. This tells us that the rate of ionization of ethanoic acid is equal to the rate at which the ions rejoin to form molecules. Ethanoic acid ionizes partially in water. There is equilibrium with ethanoic acid molecules and its ions. Some of the ethanoic acid molecules form ions. The others remain as ethanoic acid molecules drifting in amongst the water molecules. Weak acids partially ionize in water. Many molecules remain intact as molecules, HA. A few of the molecules ionize to form H+ and A-. Since chemical equilibrium is set up, we can write an equilibrium constant for this reaction. The value of Kc at 25 degrees Celsius is 1.8 times 10 to the power of -5. This very small value shows us that very few ethanoic acid molecules ionize in water. We call this expression for the equilibrium constant of an acid Ka. The values of Ka are determined for common acids. The greater the value of Ka, the stronger the acid. Strong acids ionize almost completely in water. Therefore, their Ka values are very large. The Ka for hydrochloric acid is 1.3 million, whereas the Ka value for ethanoic acid is 0.000018. Sulfurous acid is a weak acid, whereas sulfuric acid is strong. Similarly, nitrous acid is weak and nitric acid is strong. The strong acids are the inorganic acids: hydrochloric, sulfuric, and nitric acid. Many weak acids are organic acids. Many fruits, besides citrus fruit, contain citric acid. Lactic acid is found in sour milk. Ethanoic acid gives the characteristic smell and taste to vinegar. However, remember that some inorganic acids are also weak acids: sulfurous acid, carbonic acid, nitrous acid. We will now move on to find out how strong acids differ from weak acids in the way they behave and interact with bases. Here is the apparatus that we use to measure the conductivity of a solution. We have two beakers, each containing a 1 mole cubic decimeter solution of unknown acids. One a strong acid and the other a weak acid. Which of these beakers contain sulfuric acid? Remember that sulfuric acid is strong. How does conductivity relate to the strength of an acid? The Ka value is very high for a strong acid because there are high concentrations of ions in solution. Sulfuric acid has a much higher Ka value than carbonic acid. Here are the results of the conductivity experiment. The current through the beaker on the left is much stronger. The glow burns brightly in this circuit. This is the beaker containing sulfuric acid. Stronger acids have higher conductivity because there are more ions in solution in a strong acid than in a weak acid. The pH of a solution is an indicator of the hydronium ion concentration. Methyl orange indicator distinguishes solutions of low pH. It is red in a strong acid when the pH is below 3.7. At pH above 3.7, methyl orange is yellow. We confirm that the beaker with the higher conductivity is sulfuric acid because methyl orange indicates its pH is lower than 3.7. There is another way to check which of these two solutions contain the strong acid. Do you remember that the concentration of a reactant affects the rate of reactions? The solutions in these two beakers have the same concentration, 1 mole per cubic decimeter. But one of them is a strong acid and the other is weak. The strong acid has a higher concentration of hydronium ions. What do you expect to see when the same amount of sodium bicarbonate powder is added to each beaker? There are more hydronium ions per unit volume in the strong acid. Therefore, many more collisions take place per second in the beaker with the strong acid. The rate of reaction is greater in the strong acid. Let's recap quickly. Strong acids ionize almost completely in water. They have a high concentration of H3O+ ions. High conductivity. pH less than 4 and a higher reaction rate than weak acids. Now, let's consider strong and weak bases. Which of these bases is strong? The strong bases are sodium hydroxide, potassium hydroxide, lithium hydroxide, and calcium hydroxide. Magnesium hydroxide, ammonia, ammonium hydroxide, sodium carbonate, and sodium sulfite are weak bases. Strong bases dissociate completely in water. A sodium hydroxide pellet breaks from its crystal structure into sodium ions and hydroxide ions when it enters water. Sodium ions are hydrated with water molecules. The negative part of the water molecules hang on to the positive ion. Hydroxide ions are hydrated with water molecules with positive poles of water molecules surrounding them. Note that sodium hydroxide dissociates in water. Dissociation does not involve the formation of ions. Sodium hydroxide consists of sodium and hydroxide ions. It does not react with water when it dissolves. It simply splits into its ions. Note that all the sodium hydroxide dissociates. For every mole of sodium hydroxide, there will be the same number of moles of hydroxide ions. Weak bases partially dissociate or ionize in water. When ammonia gas dissolves in water, the ammonia causes the water molecules to break apart by removing a hydrogen ion from the water molecule. This leaves excess hydroxide ions in the solution. However, only a small amount of ammonia ionizes in water. Most of the ammonia simply remains in its molecular form and mixes in between the water molecules. Ammonium hydroxide is therefore a weak base. The concentration of hydroxide ions is low. Sodium carbonate is also a weak base. When sodium carbonate dissolves in water, it dissociates into its ions, sodium ions and carbonate ions. Carbonate ions are able to accept hydronium ions, protons, from water molecules. Therefore, metal carbonates such as sodium carbonate are basic. An equilibrium system is set up when a weak base dissociates or ionizes in water. We can measure the extent of dissociation Kb for the system, and in this way we can rank bases as being stronger or weaker than others. Note that the conjugate base of a weak acid is a strong base. For example, CH3COO-, the ethanoic ion, is the conjugate base of CH3COOH, ethanoic acid, a weak acid. CH3COO-, the ethanoic ion, must therefore be a relatively strong base because it tends to combine easily with hydronium ions to form ethanoic acid molecules. Therefore, the conjugate base of a weak acid is a strong base. And the conjugate base of a strong acid is a weak base. The chloride ion is a weak base because it does not easily accept a proton. Strong and weak bases exhibit similar properties to strong and weak acids in terms of their conductivity. Sodium hydroxide is a good conductor, whereas sodium carbonate has low conductivity. Strong bases are better conductors than weaker bases because they dissociate almost completely in water. The concentration of ions in solution is higher in a strong base. Therefore, there are more particles which can conduct current through the solution. Strong bases have higher pH values than weaker bases. The pH of strong bases is above 10. The last question to pose is, what is the difference between a strong acid and a concentrated acid? Strong acids dissociate or ionize almost completely in water. Concentrated acids have many moles per unit volume as compared with dilute acid that have few moles per unit volume. Right. We are moving on to find out more pH and indicators.